Welcome back to channel Encoding Tech. So in this video let us see about Huffman tree, or also known as Huffman encoding. So the main purpose of Huffman encoding is to compress a file. It may be an image file or any folder, etc. As in Windows we create a zip file, similar to that Huffman is used to compress a file and to make the size little more less. So let us see how Huffman encoding works. Now let us consider we have a text file and we have a lot of text. So what we'll do is we'll write the frequency of each character in an increasing order from the smallest to the largest. Let's consider we have a text and it has characters C, D, B, space and A. Let these be the characters and let each and everything has frequency 0.1, 0.15, 0.2, 0.2 and 0.35. So here these are the relative frequency, meaning the sum of all the frequencies result to 1. So these are the relative frequencies of the characters which are there in the text. Now these frequencies have been arranged in an increasing order. So now using Huffman tree we will try to place all these things in a tree like structure. So step 1 is to combine the minimum 2 characters into one node, one branch of a tree. So that would result in giving us a frequency of 0.1 plus 0.15, which is 0.25 as the frequency, with C being on one side and D being on one side, which it has frequency 0.1 and then 0.15. So these two together has frequency 0.25 and these are relative frequency. Now with this as one node, let's try to again arrange the things in an ascending order. Now the arrangement would differ. Now we would get characters B at the first place, then space, then followed by this tree 0.25 and then finally with A. Now the frequency would be here 0.2, 0.2 and here this can be further C with 0.1 and D with 0.15 and then A 0.35. So this here is the second part, input for the second one. Now again, as similar to before, we have to again merge the last two. Here these two have relative frequencies 0.2 and 0.2. Now adding those frequencies we will get 0.4. So that would be 0.4 with B on one side having frequency 0.2 and then having space on the other side having frequency 0.2, which results in total frequency of 0.4. Now again we have to rearrange the blocks. So on rearranging the blocks we get first the A as it has 0.35. So A with relative frequency 0.35 and then we have this block 0.2. No, first we have 0.25 with C and D, with C being on one side, D being on one side, 0.1, 0.15. So this is our first block, and then we have A with frequency 0.35 and then finally we have this block of 0.4 frequency with B being on one side with frequency 0.2 and then space being on another side with frequency 0.2. So now we have these three blocks. So now again the task is to merge the first two characters. So on merging these two, we get a frequency of 0.25 plus 0.35, which is nothing but 0.6. So now again we will get 0.6 with 0.6 on one side. We have 0.25 which has been spread over C having 0.1 and then a D having 0.15, and then on the other side we have A with frequency 0.35. And then obviously we have this part 0.4 frequency, which has B on one side having frequency 0.2, and then again space on the other side having frequency 0.2. Now since these are the only two elements, we have to merge these two again. On merging these two, we get a frequency 0.4 plus 0.6, which is nothing but 1 with 0.4 on one side. This 0.4 is also divided into B, which is having 0.2, and then space, which is having 0.2. On the other hand, we have 0.6, which is also spread against 0.25, which again is spread between C having 0.1 and then D having 0.15, and finally we also have on the other side A is frequency 0.35. So this here is our Huffman tree. Now how does compression works? So the compression string would be traversing from the root node to the leaf. Okay, while traversing on going towards the left side, if we take the left branch, then we have to add a 0. If we are taking the right branch, we have to add 1. So similarly here 0, 1, 0, 1, 0, 1. So these markings should be done. So now if you want the string for B, we have to traverse from the root to the leaf of B. So on traversing, we go to the left side, so add a 0, and again for another B we have to go towards the left side, so again 0. So our B would be represented by the string 0, 0. So here are some examples. Now if we have a letter D, let's take the letter D. So D would be represented, so our D is here, so D would be represented by the string traversing from the root. We have 1, go towards the right side, so 1, then move towards the left side, so 0, and then again move towards the right side, so 1. And then let's take another example for A. For A we have to traverse from the root to the leaf, so A, move to this right side, we'll get 1, again move to the right side, we get 1. So now we have these two letters. Let's write for the string DAD. So for the letter DAD, this thing would be D 101, for A which is 11, again D 101. So this here represents DAD. So in the normal file it would be written DAD, whereas in compressed or the zip file it would be written as 10111 So with this kind of compression we can achieve over 25 to 80% of compression. So few of the important things which you have to take under consideration in Huffman tree is, it's so beautiful that for the characters with high frequency, the code length would be minimum. So example, A has large frequencies. A here has large frequency 0.35, and therefore it has a code length of 2, which is small. And example here, C has only frequency 0.1, which is very low, and therefore has the code word length more, that is, it has 3 characters. So this is another nice thing. So that higher frequency, lesser code length. Code length is here nothing but the compression string that we get after the encoding. So how to get to know our compression ratio? Compression ratio is given by 1 minus bits per character divided by total number of bits. So here 1 minus code length into frequency divided by max code length. So here we can write it as 1 minus, so code length into frequency. Example, here A has 2. So what it would mean is A has frequency 0.35 and it has length 2. Similarly, we have for D. D, it takes 0.15 frequency and it has 3. And similarly, C, it has code length of 3 and has frequency 0.1. Similarly, space, it has frequency 0.2 and then code length of 2. And B, also it has frequency of 0.2 and code length of 2. And then maximum code length here is 3. So that would be written. So on calculating these things, we get 1 minus 2.25 divided by 3. 2.25 divided by 3. So this gives a compression ratio of 25%. So this is how we calculate the compression ratio. If you have liked this video, please do like, share and subscribe. Thank you.